All right. Well, thanks. We're really happy to have Jeff Greensite all the way from San Francisco, and he's going to tell us about the Higgs phase as a spin glass. So, take it away, Jeff.
Okay, thank you. As it says here, this was worked on in collaboration with Kazuo Matsuyama. So, what I'm going to talk about is basically two things, vaguely related. One of them, I want to talk about the distinction between the Higgs and confinement phases of gauge-Higgs theory. Then I have to bring up this concept. And then I want to talk about the possibility that fermions, for example, in a gauge-Higgs theory, for example, the electroweak, for example, superconductors, might have a spectrum of excited states. And I'll try and get to the evidence for that. Okay, the first question is this: what's meant by the phrase spontaneously broken gauge symmetry? If you open up a textbook, almost any, there's a chapter or at least a section called spontaneously broken gauge symmetry. And of course there's no such thing. There's a theorem that says that you can't break a local gauge symmetry spontaneously. There's also the Franken-Schenker-Osterwalder-Seiler theorem, which says that there's no thermodynamic transition which absolutely separates a gauge-Higgs theory in which the Higgs is in the fundamental representation into a Higgs section and a confinement phase. You can't make such a thermodynamic oscillation. Second question is, what do you mean by the word confinement even in a theory like QCD, where matter is in the fundamental representation of the gauge group? Because in theories like that, all of the order parameters for confinement which are associated with pure gauge theories have non-confining behavior, things like large Wilson loops, Toft loops, Polyakov loops. Center symmetry is broken explicitly. These all have, apparently, non-confining behavior. I mentioned the Friedkin-Schenker-Osterwalder-Seiler theorem. What it says is this: suppose you have a gauge-Higgs theory, let this be the Wilson coupling, and this is some sort of Higgs coupling. The theorem is that you can go from a region which looks like QCD, where you have flux tubes and then string breaking, into a region which looks like the weak interactions, where there's no flux tubes, no string breaking. What's more, physical states, both in the Higgs region and the confinement region, are all color-neutral states, much like QCD. So again, how do you distinguish between these? So I think the consensus view, if you would ask most people, is this: confinement in a gauge plus matter theory, where matter's in the fundamental, can only mean that the particles in the asymptotic spectrum are color neutral. Any physical state is gauge invariant. Color neutral is something different. They're all color neutral. And I'm going to refer to that property as color confinement, or C confinement. Because if you sit close to such a thing, you can't detect any long-range electric field emanating from it. Secondly, there's no such thing as spontaneously broken gauge symmetry. The Higgs part of the phase diagram, the confinement part, are part of the same Higgs confinement phase, or massive phase. And I think both of these views are wrong, and I'll tell you why. First of all, there does seem to be a physical distinction between the Higgs and confinement phases. Both phases have C confinement. I mean, their physical states are, assuming that, let's say you're in an SU2 gauge Higgs theory, for example, all of the asymptotic particle states are color neutral. Still, there appear to be some qualitative differences. In the Higgs phase, for example, there's only Yukawa forces, there's no linear Regge trajectories, there's no flux tube formation, even as metastable states. And that differs from the situation in the confined region of the phase diagram. And the question is, can we make this precise? Is there even a sharp transition between confinement-like behavior and Higgs-like behavior?
Sorry for naive question. So by saying SU2 gauge Higgs theory, the Higgs phases, you mean the Higgs scatter wave, right?
Higgs is what?
Higgs scatter wave, vacuum excitation value, and then
well, you know, the Higgs In certain gauges, like unitary gauge, the Higgs always gets a VEV.
Yeah.
It's a bad way of thinking about it, frankly.
Okay.
Yeah. Suppose I go to unitary gauge, and the only thing that's fluctuating is the modulus, and the modulus, that's always going to be positive. No matter what part of the phase diagram you're in, the Higgs would always pick up a VEV in that phase.
Okay.
However, in other gauges, no. And I'll say something about that later.
Can I ask about flux tubes there?
Yeah.
So Nambu found these metastable flux tube states.
Yes.
I thought you're saying that they don't exist, or maybe I read the
No, I'm
slide
talking about electric flux tubes, color electric flux tubes. So you're talking about magnetic flux tubes. I'm talking about the electric ones. All right. Now, to start talking about this, I begin with asking, what's the binding energy of a proton? That's a kind of a silly question, right? Or a JXI, any hadron. Now, with the hydrogen atom, we know exactly what we're talking about. You have the electron, the proton, you can separate them. And the difference in energy between this and this will give you the binding energy. Quarkonium is, of course, different. Suppose you have, some heavy quark-antiquark pair, and you try to separate the two. You won't separate them, right? You'll end up with a couple of quarks and antiquarks and then some big cloud of hadrons in the middle. However, what I want to point out is that there are physical states in the Hilbert space which do correspond to color charges which are very far separated. Now, in this case, they're not. This is close to this is close to this, everything in here, they're not separated. But there are states in the Hilbert space which are. You can certainly construct a state. Well, for example, think of real QCD. These have fractional charges, right? There are states where you could, for an instant, find that there was a fractional charge here and a fractional charge there. These things are not screened by other quarks. Now, of course, a state like that is not an eigenstate of the Hamiltonian or anything, and it would very rapidly decay into this situation. Nevertheless, there are such states. And we can ask ourselves, what's the energy of such states if you take the quark-antiquark very far apart? So we'll consider states like this. There's a ground state, and we have an operator here and an operator here. That's going to create the static quark-antiquark pair. To ensure gauge invariance, you have to put some operator between them, which transforms bicovariantly. And the question is, again, once you've specified V, you've specified what the state is. If I consider the expectation value of the energy above the vacuum energy, how does that behave as the separation between the quark and antiquark go to infinity? Well, I would say that a gauge theory has the property of what we call separation of charge confinement. S for separation, C for confinement, SC confinement. If in the limit, as R goes to infinity, this expectation value of the energy goes to infinity also, for every V, every V. I mean, you can get this property with certain V's even in electrodynamics. If you would run a Wilson line between an electron and a positron and take them far apart, the energy of such a state would go to infinity. But you can find V's, and I'll write one down later, which don't behave like that. So this has to be true for each and every V. The important point is that that V now depends only on the gauge field. If you let it depend on the Higgs field, then of course you can violate this condition because you can shield the quark and antiquark. It has to depend only on the gauge field. Now, if it has this property, we'll say that it's an SC confining theory. Okay, this I've already said. First question to ask, does this type of confinement exist anywhere in the beta-gamma phase? And I haven't defined beta-gamma, but I will later. Basically, the type of theory I'm talking about is where I have a Wilson action on the lattice. Beta is the Wilson coupling. And then if there were a piece of chalk, then there's a coupling like this. Sum over all the lengths. And for convenience, I take the modulus, you find it be 1. So then it's convenience because then there's only two parameters to worry about, beta and this parameter gamma. So in a theory like that, can you show that S confinement exists anywhere apart from beta equals 0, which is the pure gauge theory, and it simply exists there? The answer is yes. You can show, it's a long thing to do, but you can show it that in SU2 gauge Higgs theory, the theory is S confining in certain regions that you can handle with the strong coupling expansions. Doesn't mean only, yes?
Yeah, so it requires beta and gamma, I think.
Oh, okay. Beta is the Wilson coupling, which is equal to 4 over g squared, where g squared, of course, depends on the lattice spacing. Gamma, really the best, if I would write the continuum theory, I might write a lambda, eta phi, minus gamma squared. If I take lambda to infinity, which is taking the Higgs to infinity, the Higgs mass to infinity, then this gamma is the one which is right here. Okay, so then maybe S confinement holds everywhere. No, it doesn't. We can construct the operators which, in certain regions of the lattice, violate the S confinement condition.
Sorry, can I just ask? So this regime where this exists is not necessarily compatible with the continuum limit,
No,
right?
not incompatible.
Not incompatible?
Well, the continuum is often the beta goes to infinity limit. In fact, this particular limit doesn't even have a continuum limit. So it's best to think just for this particular model, where you fix
this is actually a weakly coupled regime. Okay, beta is 1 over
this
G.
this is a strong coupling regime.
Beta is 1 over g squared.
This is a strong coupling regime. Beta small.
Very small
Right.
coupling.
But that's why I'm asking, because I thought that that's why I'm confused. Because you want to take
small.
G goes to 0.
Beta small means coupling large.
Right, but
it's also where I can do strong coupling expansions.
Right, but I thought the continuum was G going to 0. That's why I'm confused.
Well,
and that would be
that's sending beta to infinity, that's true.
Right.
But I should say, this doesn't rule out S confinement in other regimes.
No, it doesn't.
It just says
it doesn't prove that it exists in the continuum limit.
Well, that's something you have to find out.
Right, okay.
Yeah.
I just wanted to make sure I'm
Something you have to find out.
Yeah.
Okay, so now the next question is, does S confinement hold everywhere, including the limit you just mentioned? And the answer is no. We can
Oops. It might just be a bad connection. Sorry about that.
Plug out, plug in again.
Touch your, sometimes it can be delicate.
I have plenty of jukes in here.
Yeah, I don't think is your computer's on?
I don't see anything on my computer either.
It might be, you know what, sometimes it takes up a lot more power than you think.
That's not the problem. The battery looks okay.
Okay, but I don't know, maybe
All right, let me
you know what,
log
it's
in
probably
again.
just that, you know what it is, it's probably just your energy saver is turning off your screen.
Ah,
And if you plug in, it probably won't.
let me do that.
Here, let me plug in. Find it. Okay, here, why don't you plug that in? Now plug this in. That should fix it.
Okay, so, and then this, it keeps asking me about, do I want edge room? How do I tell them no? All right, so, the point of these two things is we know there's regions of the phase diagram which have S confinement, there's regions which don't. There must be a transition between these two things because it's kind of an either or. You have it or you don't have it, so there's a transition. I wonder, maybe if I just turn off the internet, it might be the thing to do.
that
You
top.
can just turn off the Wi-Fi, and that should do it.
That should do it.
Pretty okay, yeah.
Okay, that should do it. Okay, now the question is, this transition, since it exists, is it associated with any symmetry of any sort? And for this I want to back up for a moment and talk about spin glasses, particularly the Edwards-Anderson model of the spin glass. This case was basically an Ising model. You have these spins which can be up or down. What's different is that you have these random couplings, which you can choose stochastically from some probability distribution. So these spins can be up or down, plus minus 1, let's say. And if you look at this is just a symmetry breaking term. It's there for technical reasons. We'll ignore it for right now. If you look at this Hamiltonian, there is a global symmetry there. Because if you multiply all the spins by minus 1, you got the same thing. On the other hand, if you look at the expectation value of the average of all spins, it's 0, because here it's up, here it's down. If you take an average, it'll average to 0. However, there is a way of defining the spontaneous breaking of the symmetry. Start out with the partition function here. Now, I stands for site. J is these random couplings. And the partition function, of course, depends on the random couplings. What could happen is that at a particular site, for a given set of spins, the spin could have a finite expectation value. It could be 0, maybe it's up, down, or maybe it's either up a little bit, the average, or down. So that's the question. Is this, on average, 0 or non-zero? So you can define an order parameter. You say, okay, let me square it. 0 squared is 0. Anything non-zero squared is non-zero. This is the order parameter, the Edwards-Anderson order parameter, and at the end, of course, we can average over these random couplings from some probability distribution.
So what's J? What's the J? J.
G?
The spin? You see the Z as a function of J. J is the coupling?
J. Oh, J. J is the random couplings.
Okay, sorry.
Yeah, J is the random couplings. Okay, so to make a bit of an analogy between a spin glass and the gauge Higgs.
Sorry, can you go back? I didn't really understand this, because this looks like, I mean, S bar squared is it's always non-negative. So you're averaging some non-negative things, so you're always going to get something positive. No?
Only on a finite lattice. If I'm in the disordered phase, think of it this way. Here's what a hand waving comes in. I have all these spins. Now the coupling between the spins is some random thing. Now let me concentrate on one spin. That spin can be up or it can be down. Mm-hmm. So I run my Monte Carlo, let's say, my numerical simulation. Sometimes it's up, sometimes it's down. But it could be that on average, it's more up than down. And maybe this persists as I take the number of Monte Carlo sweeps to be very, very large. Conversely, it could be that these up-downs tend to average to 0. Of course, after a finite number of iterations, they won't. It'll go by 1 over the square root of the number of iterations. But as the number of iterations goes to infinity, and I'm on a large enough lattice, in the unbroken phase, this guy right here, at a particular site, any particular site, will tend to go to 0. Mm-hmm. Okay. So that's the Edwards-Anderson. Okay, so we make this analogy, not saying that gauge theory is exactly a spin glass theory, but to motivate the order parameter. We will associate the spin with the Higgs field. The random couplings are the link variables in the spatial direction. Global symmetry, well, there's something called the custodial symmetry, which is rather large for SU2. At a minimum, it's the global center symmetry of the gauge group. So this is a continuum expression. We're basically taking lambda to infinity. We end up with the Wilson action plus this thing that I already wrote down. For SU2, you can take phi to be SU2 group value. It's easier to see the symmetry that way. You don't have to. So for this theory, the U's have a local transformation in the usual way. The phi's have a gauge transformation, and there's an additional global transformation, global SU2 transformation. That only exists in SU2. But in general, there is always a global subgroup of the center of the gauge symmetry, which doesn't transform the U's, but it does transform the phi's.
In things other than SU2, is that a discrete group?
Yeah.
It's discrete,
yeah,
right?
For everything
like
less than SU2, for SUN, it's Zn.
Yeah, okay, right.
Global Zn.
Okay, thanks.
Okay, you define this operator here. At 0 temperature, it would just be the ground state squared. So that defines this H. To that, we add a symmetry breaking term. This is technical. I don't want to get into it. Formally, you need to do that. And then you simply follow the Edwards-Anderson procedure. You define a Z that depends just on these U's on a time slice. Okay, you've integrated everything else out. Then you have this phi average, which depends on the U's on a particular time slice at each point. You define the order parameter in this way. I use absolute value rather than square for technical reasons. And then you can take the expectation value, and of course you need some probability distribution for that. And there's only one thing that can be. Well, it's this. Anyway, when you compare this with this, you see that what you're defining here is an Edwards-Anderson order parameter for the breaking of this, for SU2, it's custodial symmetry. For SUN, it's the global Zn subgroup of the gauge group. So if this thing is non-zero, this global center symmetry is spontaneously broken. You should understand, though, this is a non-local operator. Okay? It depends on all of the U's on a time slice, so this is highly non-local. Non-local observables can be non-analytic. Yes?
Why don't you square the 5 R's as you do on the left-hand side?
It's useful to use the absolute value, the modulus, in certain proofs. What I prove in particular is that there exists a gauge in which these 5 R's are oriented in whatever way you like. And when the order parameter is non-zero in that gauge, that's a necessary condition for the scalar field to be non-zero in any physical gauge. That's the statement. So this is kind of a necessary condition to have any kind of symmetry breaking that you're used to in a physical gauge. That's important. The gauge condition has to be expressed as some functional of the lengths. Yeah.
So,
boy, I'm never going to get through this. Okay, go ahead.
Well,
I'll get through it as much as I can.
Yeah, that's just so it's somehow there's something that's mysterious to me conceptually about this, the Edwards-Anderson model. Same thing here, which is that naively, somehow in the Edwards-Anderson model, it's like you're doing the average in a certain order, right? Like first of all, you are averaging over the J's, right, at a fixed site, and then, so that's somehow the trick, and then you're taking some thermodynamic limit there before you go to the next step. So what I'm asking is that now for and there, conceptually, there are two different averages.
I understand what you're saying.
You understand what I'm saying? But
So,
here,
yeah,
there's one path integral. You're supposed to integrate over the u's, you're supposed to integrate over the phi's, and yet it seems like it's crucial that you're integrating over them in a certain order. So there's something...
Okay, let me answer that.
Yeah.
The answer is that gauge-Higgs theory isn't really a spin glass. There is, however, I use this, okay, to define an order parameter. That doesn't change the theory. It's just a particular way of defining the order parameter. Okay. So I have an order parameter. It's completely kosher. It depends on the links on a time slice. That's all it depends on. And that's something which can be evaluated, this quantity here. This can be evaluated in an ordinary path interval. That's the point. So please, I'm not saying that gauge-Higgs is a spin glass, because there is a distinction between quench variables and the others. But for the purposes of defining an order parameter, that's what I use.
Okay, thanks.
Okay, then there's this P of U that I mentioned. So here's the point. When I take the appropriate limits, first the volume goes to infinity, then there's a symmetry breaking term. When this order parameter equals 0 in the thermodynamic limit, I have an unbroken symmetry. That's defined by that order parameter. An unbroken global Zn symmetry, which does not affect the link variables. When it's greater than 0, that symmetry is broken. It's entirely analogous, at least, to the spin glass, where when this is 0, it's not a spin glass. When it's greater than 0, it is. Now, this can be evaluated numerically. And what you do is you have this number of Monte Carlo sweeps. And as I told you, in the limit that the number of Monte Carlo sweeps goes to infinity, if you're in the symmetric phase, that order parameter should go to 0. If you're not, it should tend to a constant. And that's what happens. Below a certain value, all of the data nicely extrapolates to 0. And above a certain value, it extrapolates to a constant. And then you can plot out where that phase boundary is. This is a different line. This is where a certain order parameter associated with Coulomb gauges. I mentioned that having this symmetry breaking, this spin glass type symmetry breaking, is a requirement, is a necessity for having phi be non-zero in any physical gauge. Coulomb is a physical gauge, and this is kind of an illustration. It does lie below that. Okay, so this is finally the essential result, which I nowhere near have time to talk about. The statement is that the transition to what I'll call the spin glass phase of the gauge-Higgs theory coincides with the transition from this separation of confinement phase to C confinement. Yeah, okay. So this is against the consensus views. These are our views. First of all, what's meant by the word confinement in a theory like QCD, which has matter in the fundamental representation? This would be true in QCD, which is not a gauge-Higgs theory, but which has matter. It means that the theory has the property of separation of charge confinement. And roughly speaking, what that means is it takes an infinite amount of energy to ionize the state. And what I mean by ionize is I take the quark over here, the antiquark over here, and in between is nothing but glue. There are physical states like that. The energy of such a thing goes to infinity. That's what I mean by that. And as a physical thing, if the theory has a tendency to have a flux tube, even a metastable flux tube, it's also going to tend to have linear Regge trajectories. This SC confinement is an indication that theories in that phase will tend to form flux tubes until they break, of course. But initially, that's what they want to do. Okay.
Can I ask a question?
Yeah.
About the definition of separation of charge confinement?
Yeah.
So if it seems like it's a little, is it the same as the following criteria that I could think about, especially if I'm a Hamiltonian guy, okay? I could look at states, and I'm going to require that there's, you know, a quark here and an anti-quark here, all right? But other than that, if I'm really going to do a true variational calculation, I have to let everything else be free. But then,
no, not quite.
well,
Not quite. Because, as I said, it's important that you have only glue in between these things.
yeah, exactly. But that's
You
what
have
I'm
to create
saying.
a
So
state.
that's-
So if you were
it's-
doing it, Hamiltonian this way, it's the same thing. You have an operator that creates a quark, an operator that creates an anti-quark, and then you have some operator, it's got to be gauge-invariant state, right? So the gauge-invariant state has to have this V operator that I showed
Right.
you. And that's to make it gauge-invariant.
Right.
The constraint is that that V operator should depend only on the gauge field and nothing else.
But if I'm the operator, but somehow this, I can't prevent quarks and antiquarks from popping out of the vacuum.
Of
So
course.
it's not a, I can't give a variation. I'm trying to make a variational definition of this as an ionization energy, and I don't see how you can, because you can pop
You
quark
can,
and antiquarks out of the vacuum.
no, you can always compute an expectation value of the energy. That expectation value will depend on the V operator, right?
Right.
So you have an expectation value of the V operator. So
Sorry,
you
right.
can try
you're
and
talking-
minimize that if you like.
Yeah, okay, sorry, yeah, you're just minimizing that operator.
Yeah,
And then you're,
that's not the
okay.
minimum
Sorry.
energy. The minimum state energy is you have a quark, you have an antiquark, and you have some Higgs here and some Higgs here. That's the minimum
Okay.
energy.
So yeah, so it's not really an ionization energy, it is what you said it is.
Yeah,
You've defined
it's,
it
it's
mathematically,
where I
but it's
have
not
two
interpreted as an
I
energy.
mean that I have two charges widely separated. They're not screened by anything. So they must be sources of gauge field. And the question is, what's the energy of that gauge field?
Okay. Is there a physical interpretation of the sort of the minimal V, the V that minimizes that? Is there a
Yeah,
physical-
I think so. It would be the minimal energy flux too. In fact, in QCD, you have exactly that. You have dynamical quarks, of course. And there is, when we talk about, you know, when people compute flux tubes on the lattice, right? They put these combinations of Wilson lines between them. And there is a certain combination, which is the minimal energy for states of that kind. You exclude screening them with other quarks, okay? But out of that subclass of states, what you're really getting is the minimal energy flux tube.
Okay.
That's the meaning of it. Okay, now, as I said, you can make a confining state even in QED. Just run a Wilson line between an electron and a positron. But a V like that is not the best operator. To get the right state, you introduce what we call pseudomatter operators. A pseudomatter operator is an operator which transforms like a matter field in the fundamental representation, except under the global subgroup of the gauge group. Why doesn't it transform? Because it's something which is made completely out of gauge field. And the gauge field doesn't transform under a global center transformation. And this is an example. This state you can easily check if you make a local gauge transformation of this guy. Well, what will it give you? Consider a gauge transformation of this sort. And let's separate out the zero mode. So this is a constant mode, and these are built out of non-zero momentum modes. What you can easily check is that under that transformation, you pick up only the non-zero mode part. It doesn't transform with this constant piece here. So it transforms like a charged object, except it doesn't, unlike a matter field, it doesn't transform under the global subgroup. And in fact, in QED, that's how you build states which satisfy the Gauss law, which are invariant under local gauge transformations, but which have finite energy. And what you do is you have something that creates the electron, And then you have this pseudomatter field. And you can check that this thing is completely invariant under every gauge transformation apart from the global transformation. And in fact, that's really what makes it a charged state. And what makes a state a charged state? Basically, it's charged because it has to be gauge invariant, right? Anything has to be gauge invariant. But strictly speaking, it has to be gauge invariant with respect to satisfying Gauss's law. Gauss's law allows this much freedom. You can be non-invariant with respect to a global gauge transformation and still be a physical state. And that's what you have in electrodynamics. In fact, what this thing does is it dresses the electron with a surrounding gauge field, with a Coulomb gauge field, as a matter of fact. Okay, now, gauge transformations are one example of pseudomatter field. In fact, this guy that I showed you was a transformation to Coulomb gauge. Any SUN gauge transformation to a physical gauge can also be decomposed into some pseudomatter fields and vice versa. Particularly important for me is that any eigenstate of the covariant Laplacian operator is also a pseudomatter field. You can see why. What does it depend on? It depends on the link variables. This is the lattice Laplacian here. The link variables don't transform under the global center transformation. So neither do the eigenstates. However, the eigenstates do transform under other local transformations. So the eigenstates of this lattice Laplacian are examples of the pseudomatter field, and they're going to be useful to us. Okay, now I'm getting into my second topic, excitations of elementary particles. I needed this pseudomatter stuff to introduce that. All right, we know that if a particle's charged, we'll start with this. We know in quantum mechanics, if you have a composite system, whether it's an atom or a molecule or a hadron, whatever it is, in quantum mechanics, a composite system always has, nearly always, has a spectrum of excitations. And in fact, in pure gauge theory, if you have these static sources, this stuff over here, flux tube, we know very well that this has a spectrum of excitations that have been measured on the lattice by various people. All right, but suppose you're in a gauge Higgs theory, and you pull the quark and the antiquark far apart. Well, these things are still surrounded by gauge fields and Higgs field. In that sense, they're kind of a composite object themselves. And composite objects can have excitations. So why shouldn't it be possible for these things to have a spectrum of excitations? What would that mean if there were? Well, it would look like you have more elementary particles with the same quantum numbers of the original one, but at a larger mass. That's what it would look like. Well, I don't happen to own an accelerator center, but we can do experiments on the lattice to see if anything like this could work. So once again, I consider static quarks with some V operators, and I'll consider especially V operators that factorize in some way like that. Remember, these are still non-local because these C's depend on all of the U variables. So I can consider some superposition of various V's of that sort.
Sorry, I don't understand what that factorization means. It seems like it has to somehow depend on all the all the lengths along some path.
It does.
But then what is the factorization mean?
I only mean that I can write it as a product, that's all. Each of these depends on the gauge field everywhere.
But xi of x doesn't depend on y. Is that the point?
That's right, yeah.
Oh, it's kind of like maybe xi of x goes halfway and xi dagger of y goes the other halfway.
No, I wouldn't put it like that.
No?
You're thinking of a Wilson line.
No.
No, that's not what I'm thinking of. You saw those rows I wrote down a moment ago. For an electron-positron pair, I could have something like this.
Oh, okay.
Okay, something like that. That's a factorization. But the rows, each of them depend on the A field everywhere.
Okay. Okay, thanks.
All right, so let's try it out. I'll pick some eigenstates of the covariant Laplacian. Let's let this be the transfer matrix. I'll construct some states where I have a static quark and one of these eigenstates, and again a static quark eigenstate. And I'll also consider what I might call a neutral state. Neutral in this sense, that this is neutral, completely neutral, including under global transformations, because these two states transform in exactly the same way, and so do these. So these are what I would call color neutral states. They're not charged under anything. All right, so we have these two kinds of states. And we can consider the transfer matrix, which basically evolves over one-time stuff. And you can take this is not an orthogonal basis, so you compute these overlaps. And then you just have a linear algebra problem. How do you diagonalize the transfer matrix in a small subspace? That's, in linear algebra, it's a standard problem. It's a generalized eigenvalue problem. Anyway, you can do it. And you can find the eigenstates of the transfer matrix in this small subspace is some linear combination of your non-orthogonal basis. And then you can imagine evolving these states in the whole Hilbert space. Just let them evolve. You start out with a specific state, which is an eigenstate only in the truncated subspace, but then it evolves, and it evolves in the whole space. So it does whatever it wants to do. And you can compute the energy of the state. Well, this boils down to a logarithmic time derivative. Logarithmic time derivative gives you the energy expectation value of the state that you've evolved to after a certain time, capital T over 2. If this is not instantly obvious, talk to me afterwards. But that's what it is. Well, it is almost instantly obvious. Something that amounts to you're doing something like that. And maybe I have some signs wrong or something. But anyway, the point is, the lattice logarithmic derivative will give you the expectation value of the energy of the state that you've evolved to after a certain time t. Numerically, in case you're interested in that, all that's evolved in making the calculation is you have to compute these quantities. You have to compute this, you have to compute this. So these pseudomatter operators, which are things that you ask the computer to give you, you give it a spatial configuration at a particular time. You find the eigenvalue, the eigenstates of the lattice Laplacian operator. You find a set of these pseudomatter operators. Do the same thing at a later time. Then what happens is, since you're dealing with static quarks, the static quarks kind of drop out of the problem. And what you have to do is to work out the correlator of these two Wilson lines, a Wilson line going this way, a Wilson line going that way, and at the ends you have these pseudomatter fields. So that's the calculation. Can be done. So what are the possibilities? Well, you started out with a state which was an eigenstate of the transfer matrix just in that tiny subspace. Well, it could be that you were incredibly lucky. And that state was an eigenstate in a full Hilbert space. So the energy never changes. You would have to be very lucky. More likely, and the first thing you would say before you even started in this, and this would occur to you right away, and then you would stop, unless you're really dumb, like me. Well, this thing is just going to evolve to the lowest energy state. You'll never see a spectrum. All you'll see is the lowest energy. However, there is one more possibility. It could be that this one of these states, maybe one of them evolved to the ground state. Now remember, the excited states, they were initially orthogonal to that lowest energy state. So let's say the lowest energy state just evolves smoothly to the ground state. Is it not possible that one of the states that was initially orthogonal stayed orthogonal? And instead of evolving to the ground state, it evolved to some excited state? Well, you don't know this for sure. You have to do the calculation. We did it. At beta equals 5.5. This is inside the Higgs, this is inside the confining region, confining phase. This is inside what I would call the spin glass phase, the Higgs phase. This is the action that I've already written. First thing you do is you look at the energies of these states constructed out of phi 4 and phi 1. And what do you see in the confinement phase? Well, in the confinement phase, the state you construct out of this is a color-neutral state. You shouldn't expect the energy to rise, keep on rising. After all this corresponds to is a quark neutralized by a Higgs, another quark neutralized by a Higgs, take them as far apart as you like. And that's this green line. What if instead I have the quark with a pseudomatter operator and a quark with a pseudomatter operator? Remember, that's antiquark V quark. That's Q bar V Q. And if it's in the separation of confinement state phase, then that energy, if separation of charge is correct, that energy should keep on going up linearly to infinity. And that's exactly what happens. And of course, these things should be orthogonal, and they are. This is the overlap of those two states. Changes completely in the Higgs phase. In the Higgs phase, both of these two phases are, well, you can pull them apart. It doesn't cost much energy. And they have a very large overlap with one another. All right, those are states constructed of phi 4 and phi 1. Now we look at the states which I constructed to be eigenstates of the transfer matrix. And I'll evolve them. I won't show you all what happens at less than 4. But I evolve them for various units of time. And I don't start out here. These points start out here, and these points start out here. They start out at different places. But after a few time steps, they converge. The energy for the state derived that I get by evolving psi 2, those energies lie here. And the energies that I get by evolving this state are down here. And the overlap between these two states is essentially 0. So this is evidence that I'm finding an excited state. Now you might ask, well, maybe you're just finding the ground state plus a gluon or something going off. Or, whatever the vector boson is in this area. We check that. It's the gap here is much smaller than what's required to create an excitation flying off. So this is actually evidence for a single isolated charge in an SU3 gauge Higgs theory having a spectrum of excitations, at least one excitation. Well, I guess I'm doing better on time than I thought. Can also talk about the Landau-Ginzburg model. I have until 2:30, right?
Yeah, can I ask a question about the previous thing? So I'm a little confused about, so if I have any state, of course I have excitations, right? I mean, because I can just add a particle or add anything, right? So, but you have something more specific in mind.
Yeah,
here.
I have
So,
in mind eigenstates.
eigenstates, but eigenstates of energy, I can just add something that adds some energy. There's
Well,
some,
think about QED for a moment. Are there such things in QED that have an electron and a positron? You might say, well, can I disturb the system and add some energy? And the answer is, of course I can. But what you get in that situation by adding that energy is you get a bunch of photons flying off.
yeah.
You don't get
Yeah, that's what I'm confused. I mean, I think you have some additional requirement for what you're calling an excitation that I didn't understand.
Well,
You
what
have
I'm
some- you
saying
have
is
some
that
additional
there is an eigenstate of this system.
an
It's
energy
not the lowest
eigenstate.
energy eigenstate, and it's not the state plus a vector boson. That's the statement. Because of course you can add any number of vector bosons you want.
Right.
You
So
can
how
distort
do you
the field
check-
any way you want, but what happens as you let it evolve in Euclidean time, right? As you let it evolve in Euclidean time, you'll either go to the ground state if there's an overlap with the ground state, or you'll go to a state with some number of vector bosons. Now what I'm saying is that in this system, there is an excited state, in fact an eigenstate as far as I can tell of the Hamiltonian, which is not that thing. It is not the ground state plus a vector boson or some collection of vector bosons. It's not that. It's a stationary state. So what would happen is you have a particle here. You give it some energy. Maybe some vector bosons fly off. What you can end up with is a stationary particle. Nothing is happening, but its mass is greater than the particle you started with. Okay.
Yeah, maybe I'll ask later. I'll think about it.
Okay. All right, so you can do something like that also for the Landau-Ginzburg theory. It's a non-relativistic theory. It's different from the abelian Higgs theory in that this time-like piece has some gigantic constant in front. Anyway, you can play the same game. And I won't go into details, but what you define indeed is, first of all, the lowest state is right down at the bottom. I didn't even show it. The first excited state, in fact, does correspond to the static electron plus a massive photon. This is at a superconductor. So these purplish dots here are ground state plus massive photon. But then there's this state. There's some different colors because these were done in different volumes and scale and so on. But anyway, but this state and these states cannot be interpreted as just the ground state plus some photons of some definite momentum. They do not have that interpretation. And here it's important. The reason I can say that conclusively is it's a finite lattice. And you can't fiddle with the momentum infinitesimally. It has to change in chunks. So you can figure out what those chunks are. And you can show that giving your zero momentum vector boson, photon really, whatever momentum, it won't land up here, it'll land up here somewhere. So the question is, the obvious question is this observable? Well, maybe. We're, as it says here, we're a long way from doing anything accurate, but in principle it could be done using X-ray photo emission spectroscopy. And in fact, you can even argue, that the sort of effect I'm talking about has already been seen in ordinary metals. I'll explain that in a second. So here's what's going on, normal metals. Photon comes in and knocks out, this is an ordinary metal, knocks out a core electron which is bound to the atom. And that suddenly creates a charge. Now in a normal metal, the conduction electrons will rearrange themselves to screen that charge. But in the screening response, there is a nearly continuum excitations of the Fermi sea. And if this Fermi sea is left in an excitation above the ground state, then that reduces the energy of the electron which is flying out, which is detected. And that in turn affects the line shape of the photoelectron spectrum. So I want to emphasize this is the sort of thing I'm talking about. Huh? This hole, you knocked out an electron, you got a hole there. The hole can't just sit there all by itself. It's going to be surrounded by something, these conduction electrons, and of course the electric field. These conduction electrons can, in principle, vibrate. Can have a spectrum of excited states. And if it's left in an excited state, of which there are very many in a normal metal, then this affects the energy of the photon coming out. And this is the origin of something called the Doniash-Sunjic line shape. I mean, these things have been done, of course. Here you're measuring how many counts you've got of electrons of different energies. And it's somewhat asymmetric. And these guys, Doniash and Sunjic, wrote some sort of classic paper where they explained the shape, and they explained it with exactly this logic, that these photoelectrons which are emitted below the maximum correspond to where you actually shake up the Fermi sea that surrounds it. Now, what we would expect in a superconducting phase would be a little different. There we would expect screening from the Cooper-Pairs condensate. And we think that the excitations of this condensate, because after all, if this is described anything like Landau-Ginzburg, it's exactly the sort of thing we looked at. So what we ought to see is additional excitations, not just the main peak, but maybe some others. That would be different from what you see in a normal metal, because in a normal metal you have this near continuum of excitations of the Fermi sea. So what's really needed is a comparison of the core emission spectrum in these X-ray photoemission experiments, a comparison between the spectrum in the normal state and the superconducting state. And you would think this had been done. I talked to some experimentalists. I did what I could to look at the literature myself. I can't find any such comparison. So I would love if somebody who had the skills to do these kind of things would do it. Because it would be an interesting test of these ideas. So conclusions. Statement is that the gauge Higgs fields surrounding a charged static fermion have a spectrum of localized excitations, and they can't be interpreted simply as the ground state plus some vector bosons flying off. That means that elementary particles, quote unquote elementary, in theories of that kind, can have a spectrum, can have a spectrum, a mass spectrum. There would be more particles. And it seems to be pretty robust. We looked at it at Landau-Ginzburg, abelian Higgs, SU3, also some butchery of a chiral gauge theory. And in all of them we saw basically the same thing. We always saw these excitations. What about quarks and leptons? Real quarks and leptons. If we had a lattice formulation of chiral gauge theories, And that's a tall order. Nobody knows how to do it. And we need a positive transfer matrix and a continuum limit and all of that. If we had that, then perhaps we could figure out the masses above the ground state of the quarks and leptons. Well, we don't have a lattice chiral gauge theory. It would be nice if we did. I'll stop there.
Any questions?
Out of curiosity, what is one thing that we just can prove between the like equivalent of quantum field theory and lattice? Like, what is?
Oh, well, that's a big question. You're asking me how do we prove the equivalence of lattice and continuum quantum field theory? I think a true lattice theorist would tell you there's no such thing as continuum quantum field theory. I mean, just look at it. What are you doing? Subtracting infinity from infinity and then multiplying something by infinity? You know, a mathematician would say, what the hell are you talking about? It doesn't exist. Can you give me something that really exists at the non-perturbative level? Of course we can do Feynman diagrams. And everybody knows that those Feynman diagrams, that expansion blows up. So what do you really mean by continuum quantum field theory? So lattice theorist, and I'm not really one, I play one on TV. A true lattice theorist would say, there's no such thing as continuum quantum field theory. What you have is lattice theory, which approaches the continuum limit. And then you can show things like, okay, Feynman diagrams and lattice gauge theory give you the same results as continuum perturbation theory. It's a big, big mess, you know, because lattice theories have all these extra interactions that you need. But eventually, at the end of the day, that's what you get. So you can match them perturbatively. Non-perturbatively, well, you know, in the continuum, you know, that's where instantons were discovered. Okay, you can find those on the lattice too. So, knowledge. But nobody worries about it too much either. Yeah.
I may have just missed this part earlier in the talk, but at the beginning you were setting out a result that there's no like thermodynamic phase change between this confinement-like and this Higgs-like phase.
That's right.
But you're saying that when you define confinement as like what is the limit of the energy as they become separated to infinity, then there are distinct
Correct.
phases.
What I'm saying is that there's a distinction between those two phases, even though when you cross the phase boundary, you don't necessarily have a thermodynamic phase transition. Now that's actually, it's actually not unique to quantum field theory. This is known in condensed matter. There's such a transition called the Cortez phase, Cortez line, where there's a certain line and a certain formulation of the Ising model, don't ask me the details, but there's a physical distinction between two phases of the Ising model and an external magnetic field, and yet there's no thermodynamic transition when you cross the line. So it's not unknown.
Okay.
Also, you might say, well, how can you have a phase transition? You know, what's non-analytic? Local stuff has to be analytic, but non-local operators can be non-analytic, and that's what's going on here.
Which operators are non-local?
Remember this Edwards-Anderson, this Q of J and Q of U thing I showed you?
Oh, okay.
That's non-local.
I think my understanding of this, though, is that, I mean, this theorem that you quoted is a theorem. I mean, it's true, right?
Yeah.
And so the thing is that it's what it. But if you state it very carefully, what it says is that basically anything that you can any operator that you can compute by just averaging over the path integral can be continuously deformed,
Well,
isn't that right? And
any
so, but
local.
then what?
Any local operator.
Well, so I thought, so local is, because I thought for your thing,
No, it's
the
not
crucial
just
thing is
any-
that you're doing this trick where you're doing the average in this way that's different from the path integral.
Sure, sure. But at the end of the day, what I'm introducing is an operator, just a normal operator that depends non-locally on the gauge field. Okay, and then you're taking the expectation value of this operator. Never mind how I defined it. I defined it in some complicated way that looks like a spin glass. At the end of the day, I end up with an operator that just depends on the gauge field, non-locally. And then the Osterwalder-Seiler theorem, because they're the ones who actually proved it. The Osterwalder-Seiler theorem does not actually apply to operators of that kind. It requires, one of the things that goes into it is locality. There's plenty of other examples. When you look at, for example, when you compute, for example, the expectation value of the Higgs field in Landau gauge or Coulomb gauge, there again, you get this sort of non-analytic behavior. And again, it has to do with picking that gauge choice, in effect, makes the operator that you're computing non-local. Because one way of phrasing it would be to say, okay, what I'm really computing is I'm computing gauge transformation times scalar field, let's say. That's the operator whose expectation value you're taking. And that operator is non-local. And it's very well known that, you know, there's a phase where it's zero and a phase where it's not zero. So it's another example, the same thing.
So we shouldn't worry about thermodynamic phase transitions.
Well, I don't know, it depends on the context. Sometimes we should, sometimes we shouldn't. In this situation, what I'm trying to say is that the thermodynamic phase transition, the existence or the lack of it, is not the defining factor. The defining factor is the loss of S confinement going to C confinement.
So if I take the standard model and I have an electron, then there should be an excited electron.
Yeah.
What's the scale of the excitation?
Oh, I wish I could answer that question. I would say that it's probably, just judging by everything else, I would guess it's on the order of the Z mass. But I can't tell you anything more precisely than that.
You said muon now. So.
Same thing. It would be presumably we're looking at excitations on the order of the Z mass.
I mean, I kind of had similar question, but stated maybe more theoretically. I mean, are these what you're calling excitations? Would they be what we would call bound states, or in other words, would they, you know, so if the traditional way of looking at things, I look at the spectrum of the Hamiltonian at spatial momentum equals 0, and then single particles are isolated states, right, and multi-particle states are continua. Would these things show up as, how would these things show up? Would they show up as particles?
They would show up as particles.
So they are particles.
Yep.
They're particles. So you really would be predicting that there's another particle.
I'm really predicting that there's another particle. What their lifetime is, what their mass is, anything about them I can't actually say. Except I think they're there and that's all I know.
Wow.
There's an electron, there's a muon, and there's a tau.
Yeah.
And now you have a theory of them.
Oh boy, yeah. I love that. Yeah. Of course, that's the first thing you think of.
Yeah.
The generations are precisely that.
Well,
Then I start worrying about flavor-changing neutral currents and things like that.
How about
I
the
haven't been
quarks?
able to see why they
Would
wouldn't.
decay to each other.
Yeah.
I don't know.
Yeah. Then I worry about things like that. Otherwise, I have a great candidate for generations.
So I didn't really, to be honest, I didn't understand your procedure for looking for these excited states. But you're predicting that if somebody just was getting the spectrum of these theories on the lattice, that they would find these additional kind of unexpected bound states, if you like. I could call them that if I...
I wouldn't call them that, I would call them excitation. But anyway, the answer is yes. That's what I would expect.
Okay,
Of course,
excited
I can't tell
states,
you-
excited
I can't tell you their
particles.
width, it's probably enormous, but they should exist.
But they're just bound states in the sense that they're below the two-particle threshold, for example.
Yeah.
Okay, so in that sense, I think
Yeah,
you
they're,
would call
that's
them
right.
bound
They're below
states.
the threshold.
Yeah,
That's right.
okay. Other questions?
But for going back to SU2, you wouldn't say that so you have our electron, there's an excited electron, it has to have the same gauge charges, so it's not like
It would have the
bound-
same quantum numbers.
it doesn't have the same quantum numbers as an electron and a gauge boson, because they have SU2 quantum numbers.
No, I would say that we're looking at things with the same, could you change the spin, maybe? I haven't thought about that.
But the same
So-
gauge charges, certainly.
But they would have the same gauge charge,
Well, let's thank Jeff for a provocative, interesting talk.